Star formation is one of the most important problems in astrophysics. I see it as being at the nexus of astrophysics. If you want to understand how galaxies evolve, galaxies consist of stars, so it really comes down to then how the stars evolve. If you want to understand where did the heavy elements in the universe come from, those heavy elements are made in stars, so we have to understand how the stars form. One of the most active fields in astronomy today is the study of exoplanets, planets around other stars. Planets form around stars. You cannot understand how planetary systems form unless you understand how stars form. So it's really one of the very basic questions. It's important to realize that the sun was formed about 4.5 billion years ago, but the star formation of the galaxy continues today. It's been gradually decreasing over the last 10 billion years, but we still make about 1 or 2 solar masses of stars per year in the galaxy. These stars are formed in molecular clouds. The molecular clouds are large regions of gas. Many of them, in fact, much of the molecular gas is in so-called giant molecular clouds, which can have sizes up to 100 parsecs, or that's 300 light years in size. And this gas is dense by interstellar standards, can have densities of thousands of particles per cubic centimeter. They're very dusty, that is, they have tiny particles which absorb light. And that's very important because, first of all, the molecular hydrogen in these molecular clouds is actually formed on the surface of these dust grains. And secondly, the dust grains tend to block the ultraviolet radiation which could destroy the molecular hydrogen. So it's very important for the gas to be able to be shielded like this so that it can be molecular. The molecular gas being shielded is also very cold. The typical temperature is order 10 Kelvin. So first let me talk about how low-mass stars like the sun, for example, form. What you need to do is you have to have a region of gas in which the force of gravity can exceed the forces associated with pressure. So an easy way to think about this is just in terms of energy. I can just ask, if I look at a region of gas, I calculate its gravitational energy, and I calculate the energy that it has in thermal energy, just due to its heat, then I can say, well, which one is bigger? If the gravitational energy is bigger, then at least in principle, I can go ahead and undergo a gravitational collapse. And I would start off, as I mentioned, at a density that's measured in particles per cubic centimeter, and then by the time you actually form a star, you have densities measured in grams per cubic centimeter, 24 orders of magnitude larger than in particles per cubic centimeter. So one of the things that happens, though, is that while this gas is contracting, it also has some angular momentum. So just as the classic example of an ice skater who is spinning on the ice with her arms outstretched, as she draws her arms in close, she will spin faster and faster because you conserve angular momentum. Similarly, if I have a gas cloud, and even though it's rotating very, very slowly, as it contracts, it too will spin up. And as a result, while you will get a central star, you'll also get a disk of gas around that. And in fact, much of the gas that feeds into the star might first fall into a disk and then gradually accrete from the disk, through the disk onto the star. And this disk toward the end of the formation of the star is very important because that is the site of planet formation. Now, another very important constituent of the interstellar medium is magnetic field. And there's a problem. When I have this magnetic field threading the gas, if the field is too strong, it might be stronger than gravity. So you know from Newton's laws that the energy in the gravity that I have, say, in a blob of gas goes like the square of the mass divided by the radius. Then you can use Maxwell's equations and you can show that the magnetic energy in that same gas goes like the square of the magnetic flux divided by the radius. So they have very parallel relationship, and it basically then depends on the ratio of the mass to the flux. If the mass to flux ratio is large enough, then gravity wins and you can overcome the magnetic field and form a star. If the mass to flux ratio is too small, then that means the magnetic field is stronger than gravity, and you cannot form a star. So obviously, in order to get the star, then we have to be in a region where we have the mass to flux ratio being large enough. And there's been a big debate in the astronomical community about what this ratio is on the theoretical side. Observations now seem to show clearly that typically the mass to flux ratio is large enough so that gravity can overcome the magnetic field. But our problems are not over. I mentioned that as the gas contracts, it spins up, and as it goes smaller and smaller scale, it spins more and more rapidly. However, if I have the magnetic field, and then it starts being dragged around and getting turned into a corkscrew shape, that then exerts a torque on the gas. It actually tries to stop the gas from spinning up. In some of the very first calculations which tried to follow what happened when the gas contracted in the presence of a magnetic field, they found that the magnetic field was so strong that you could not form a disk at all. And this is a direct contradiction with observations, since we see disks around stars when they're forming, and we know that there was a disk around the sun, since we have planets around the sun, and as I mentioned, we have planets around other stars as well. There's been a very large study in the first decade of the 21st century studying how the magnetic field can affect the gas when you include more physics. In particular, when you include the turbulent motions which are observed in all the gas in the interstellar medium. And now it appears that, in fact, it is possible to overcome this. Despite the magnetic field, you can form a disk. So let me now talk briefly about how massive stars form. Massive stars are very important because they're the ones that are responsible for the formation of the heavy elements. In particular, stars more than about 8 solar masses undergo what's called a core collapse supernova explosion, in which after exhausting its nuclear fuel, the core of the star contracts and then explodes in a titanic explosion, ejecting heavy elements into the interstellar medium. How do stars like that form? There are two competing theories. One is called competitive accretion, and that says that you have a number of stars forming in a cluster, and the star that is more massive then will have a stronger gravitational force on the surrounding gas, so it will be able to attract more gas to itself and therefore grow faster and become a larger star. Another model is called the turbulent core model, and what that says is that actually you have regions of gas which are internally turbulent but nonetheless are gravitationally bound, and these turbulent cores then can contract and form stars. So to some extent that's just a blown up version of the low mass star formation picture that I described earlier. And there's a lot of both theoretical and experimental work underway now to try to understand it. I imagine that when we get a much better understanding of high mass star formation, there'll be aspects of both of these theories and perhaps new ideas that will be incorporated. Now, one of the most important properties of massive stars is that they have very high luminosities. There are stars that are observed that have masses up to about 100 times or even a little bit more times the mass of the sun. But the amazing thing is that even though the mass increased by only a factor of 100, the luminosity increases by a factor of over 1,000,000. So in the case of the sun, the effect of the radiation does not very important dynamically. When you increase this radiation by a factor of 10,000 or 100,000 or even 1,000,000, then that can be so strong that it can actually push on the dusty gas around the star and prevent the star from forming. And a very simple calculation, in fact, suggests that stars cannot form if they're more massive than about 17 solar masses. But as I mentioned, we observe stars that are more massive than 100 solar masses. So clearly there's something wrong. Theorists have come up with several ideas to explain this. One is that, as I mentioned, the gas tends to collapse into a disk. And so that means that it's a lot easier for the radiation to escape above and below the disk, and then the gas in the disk can come in. Another a fascinating aspect of stars when they're forming is that they actually eject mass. So whereas astronomers in trying to observe star formation were initially looking at regions of gas that were undergoing collapse, the first thing they saw was gas that was actually coming out at velocities of hundreds of kilometers per second away from the star forming. And this then blows a cavity around the gas and makes it even easier for the radiation to escape. A third possibility, or third effect I should say, is that the radiation is pushing on this gas, and when you have a light fluid trying to push on a heavy fluid, that's unstable. It's called the Rayleigh-Taylor instability. And it's familiar to people. If you imagine taking a glass of water and, say, putting a cardboard over on top of it, or a piece of plastic, and turn it over so that the water is staying there. If you then take this away, in fact, as far as the force balance are concerned, the water could stay inside the glass. But in fact, as you know, what's going to happen is the water will almost immediately fall out of the glass. And the reason that it falls out of the glass is because very tiny ripples on the surface of the water will grow exponentially in time, and that leads to the water falling out. Similarly, when you have this radiation pushing out on this dusty gas, then if you have ripples in that dusty gas, you can have then large amounts of that gas falling in while the radiation escapes out through the less dense regions. All these different mechanisms contribute. One of the main ways of trying to study such complicated problems is through the use of numerical simulation. And researchers are using very large supercomputer codes, running them for 1 million hours, 1 million CPU hours, to do a single calculation in order to include all the physics that goes into forming stars. And that's shed a great deal of light on the processes that are involved. Now, there are several major problems that people are wrestling with. One is what's called the initial mass function. As I mentioned, we have a star like the sun, and there are some stars that are up to 100 times the mass of the sun. Well, what determines the ratio? How many 100 solar mass stars are there compared to 1 solar mass stars? Well, it turns out there's only a very tiny number of such very massive stars. I mentioned that stars above about 8 times the mass of the sun will explode as supernova. And you can ask, how many stars do I have to form in order to get one supernova? And it turns out that observations show that that is about 100 solar masses. So every 100 solar masses of gas that I turn in to stars, then I will get about 1 star that will be at least 8 solar masses. So then you can ask, well, why is that? And there's been a great deal of progress on that in the first decade of the 21st century. And it's now thought that it has to do with the turbulent nature of the gas in which the star is formed. And from you can then calculate from the properties of this turbulence how the different amounts of gas will form in different size clumps of gas. And some of these clumps will be massive enough so that they're able to overcome gravity. And by actually carrying through that calculation, you get a distribution of stellar masses which is similar to that that's observed. The second major problem in star formation is the calculation of the rate of star formation. That's really crucial. The typical density in the interstellar medium is about 1 particle per cubic centimeter. And you can calculate how long it would take a gas with a density of 1 particle per cubic centimeter to collapse if there were no forces or other effects resisting the collapse. That's only 40 million years. The galaxy is more than 10 billion years old, and we have a very large amount of gas in the interstellar medium. We're not turning all the gas into stars that rapidly. In fact, the efficiency of the star formation is only about 1% of the stars get turned, 1% of the gas gets turned into stars in the time that it takes for gas to undergo gravitational collapse. So why is it that star formation is so inefficient? It's believed that several effects contribute to this. One is the turbulence that I already mentioned, that when you have a very turbulent gas, you have both the gas being brought together in conditions of high density, which favor star formation, but you also have the shock waves going through this gas, tearing it apart and preventing the contraction. Another effect that limits the rate of star formation is the magnetic field. It's observed in these large-scale numerical simulations that I mentioned, that when you include the magnetic field, that tends to reduce the rate of star formation by a factor of 2 or 3. Then a third effect is the star formation itself, that it is self-limiting. As I start to make these stars, the stars are injecting a radiation into the ambient medium. They are injecting these outflows into the interstellar medium, and particularly for the massive stars, they have this ionizing radiation, which heats up the gas to 10,000 degrees and tends to blow the gas away. So there are a number of effects that limit it. And when you include all these effects, it's then believed that you will be able to explain the low efficiency. Although so far, early in the second decade of the 21st century, the numerical simulations are still not complete enough to get good agreement with observation.